Assalamualaikum and good morning. Today we will do a presentation about ceramic coating, and the title that our group choose is Sol Gel Ceramic Coating on Silicon Carbide Particle for Interfacial Design of Powder Metallurgical Copper Composites. Then our group members are 1 HEZMEERA AFIFAH binti 1 HEZRIL, Nur SYAMIMI ATHIRA binti ABDULL, and me myself Nur AMISHA binti MAHIZAN. Next, these are the contents that we will discuss later on by each member. As I mentioned before, this paper are focusing on looking a way to optimize the Sol Gel method on silicon carbide particle that used as reinforcing material in the copper matrices. It was found that silicon carbide could be used as a reinforcement in the copper matrix to make the composite stronger. This composite, the copper silicon carbide composite, can combine the exceptional ductility and toughness of copper with the high strength and modulus of silicon carbide reinforcement to produce a composite that is both strong and flexible. But during the powder metallurgical process of this composite at temperature higher than 800 degrees Celsius will resulting in the development of the intermetallic compound. These compounds that form in the composite are harmful to the characteristic of the composite that occur from the reaction between the copper and silicon carbide particle. So, previously we know that copper is the matrix in the copper silicon carbide composites, and we all know copper has a lot of good physical qualities and they are the most second abundant element on earth, which means it is very easy to obtain copper anywhere. They are also possess the second highest electrical conductivity and widely used in electronic and thermal applications. Other good physical qualities about copper are they have high electrical and thermal conductivity, good corrosion resistance, and high melting point. But on the other hand, pure copper has a low mechanical property at both and high room temperature, which prevents it from being used regularly. To enhance the ceramic coating process of the composite, this paper focused on using the Sol Gel method. So, what is a Sol Gel method? So, briefly, the Sol element of the Sol Gel formula refer to a solution in which the particles are suspended. The hydrolysis of the suspended particles occur as a result of the addition of water, followed by the condensation polymerization in which the molecules join together to form a gel. This is where the gel element of the name of Sol Gel derived from. When it was applied as a coating to a material surface and allowed to dry for a specific time, the Sol Gel will form a hard dense surface that has a high gloss glass-like finish that is free from any surface irregularities. Consequently, this new surface has the potential to serve as a protective barrier coating at the copper silicon carbide particle interface, which is very important for corrosion resistance. The ability to achieve a large surface area while still maintaining a stable surface is the most significant advantages of the Sol Gel method. Materials produced by the Sol Gel method are characterized by their chemical and physical properties. So, it is very important to note that when we are using the Sol Gel method, there are two main reactions that will occur, which is hydrolysis of the precursor in acidic or basic medium and polycondensation of the hydrolyzed products. Technically, we all know that it is very hard to design or invent a highly developed thermal management materials that are capable of handling specific requirements, such as has a good power density, good reliability, efficiency, and etc. So, when the new generation of materials, which is metal matrix composite that reinforced by the ceramic phase has emerged, these innovative materials combine the metal plasticity with ceramic mechanical strength. So, copper and its alloy are the ideal candidates for the application that requiring high stiffness and thermal load bearing capability. Because of these excellent thermal qualities, Silicon carbide particles are used as a reinforcement in copper matrices for the development of thermal management material system with desirable thermal properties. So the contact interface between the reinforcement and the matrix has the biggest impact that can influence the composite performance. This contact will determine the composite thermal conductivity, thermal expansion coefficient, and mechanical properties. So, an ideal contact should has an excellent adhesion and minimal thermal boundary resistance. The disintegration of silicon carbide particle in contact with the copper at specific temperature such as 1123 Kelvin and 1373 Kelvin will resulting in the dissolution of silicon into the copper. This will reduce the thermal and electrical conductivity of the composite, the copper silicon carbide composite. So, this is the primary challenge that needs to be focused in the copper silicon carbide particle composite.
The objective of this study is to improve the ceramic coating process on silicon carbide for use as a reinforcement in a copper matrix using the sol gel technique. Because of the interaction between copper and silicon carbide particle, powder metallurgical processing of copper silicon carbide particle composite over 800 Celsius resulted in the development of intermetallic compounds that are harmful to composite characteristics. Next is to reduce the interaction between copper and silicon carbide particle. Ceramic diffusion barrier coatings on alpha 400 silicon carbide particle are used. At the copper silicon carbide particle interface, the sol gel manufacturing technology has been refined to generate a fairly homogeneous protective barrier layer. Not only that, this study also was to determine the vital role of the quality aspect of the sol gel coating process and to indicate the absence of any residual process-related impurities. For the precursor surface treatment, as we know, it is prior to any coating procedure which is surface pre-treatment is considered to have an important function. As a result, alpha silicon carbide particle was pre-treated using two separate methods, which is first heat treatment and blending process using a double cone blender. First step in this process is alpha silicon carbide was subjected to heat treatment at 873 Kelvin for a stipulated duration, followed by subsequent surface activation using hydrofluoric acid. Next, in order to improvise the surface pre-treatment processing efficiency, alpha silicon carbide particle was subjected to milling in a double cone blender with ratio 10/1 as a ball to charge ratio. Hardened steel ball of a diameter about 8 mm were used as a milling media for a duration of 30 minutes. Third step was the blended and heat treated of alpha silicon carbide particle were then washed using deionized water and an organic solvent in order to ensure the removal of processing related impurity, if any. The fourth step is that the few samples were only subjected to organic solvent washing to assess the effect of water treatment on the ceramic coating properties. Last step is that the trial study will carry out to optimize the surface pre-treatment as well as the sol gel processing methodology to attain a uniform coverage on ceramic oxide coating on alpha silicon carbide surface. Next, for the sol gel methodology process will be started with the surface pre-treated. Alpha silicon carbide particle is then treated with the ceramic oxide precursor and a urea as a hydrolyzing agent in a sol gel process. To help the gradual hydrolysis of urea for a certain period, the liquid is continually agitated using a magnetic tablet in a stirrer at 353 Kelvin, maintained using an oil bath. The moisture content of the sol gel treated alpha silicon carbide particle is subsequently removed by filtering and drying it in a hot air oven. The last process that's shown in this journal is characterization of coated silicon carbide, which is the phase purity, crystal structure and surface morphology of sol gel treated. Alpha silicon carbide particle were investigated using a Bruker D8 Advanced X-ray diffractometer XRD and a AZIZ Neon 403533 dual beam scanning electron microscope (SSM), equipped with an Oxford AX energy dispersive analyzer of X-ray (EDX).
Next, we go to the result. The study yielded two important findings, which are the XRD of sol gel treated alpha silicon carbide particles and morphology studies of sol gel treated alpha silicon carbide particles using SEM or EDAX were performed. For XRD of sol gel treated by alpha silicon carbide particle, As a result, figure 1A and 1C were cleaned with deionized water and organic solvents. Meanwhile, figure 1B and 1D, they were only washed with organic solvent. The results show that the cubic and monoclinic yttrium oxide were formed. The lack of impurity peaks confirm the phase purity of yttrium oxide deposited on hexagonal alpha silicon carbide particles. The presence of rhombohedral alpha silicon carbide particles in relative low volume fraction was also confirmed. The finding confirmed the suitability of sol gel particles process methodology for the interfacial design of copper composite reinforced with alpha silicon carbide particles. For the result 2, morphological study of sol gel treated alpha silicon carbide particle using SEM or EDAX. The SEM micrograph shows that the sol gel treated blended alpha silicon carbide particle is subjected with only organic solvent that have significant coverage. From figure 2A, the thickness of the coating layer is not uniform as well as morphological, such as rise hugs as a secondary growth mechanism and local aggregate formation in figure 2B. As shown in 2C, some silicon carbide particle surface areas do not have ceramic oxide deposition. In figure 3, shows the SEM-OEDAX analysis of the sol gel treated blended alpha silicon carbide particles subjected to only organic solvent washing. The elemental analysis results show trace amongst the fluorine impurities, confirming the absence of any process-related impurity picked up in the surface treatment process methodology used. The formation of uniform layer of ceramic oxide coating as well as the formation of bubble-like feature in figure 4A was revealed by sol gel treated blended alpha silicon carbide particle washed with organic solvent and deionized water. The formation bubble-like feature was observed to initiate coating delamination, which resulted in subsequent peel-off. The non-adherence of the coating was observed as the coating thickness was increased, as shown in figure 4B, as well as 4C. It was also discovered that changes in surface pretreatment procedures had an impact on the morphology of ceramic oxide coating. It is worth noting the absence of rice-husk-like morphology in the sol gel treated blended alpha silicon carbide particle washed with both organic solvent and deionized water. In figure 5, the absence of fluoride element peaks is indicated by SEM or EDAX analysis of samples. The effect of fluoride ions on the properties of composite terms will be determined as soon as heat compaction is complete, followed by carbide particle and CTE studies on the specific copper or silicon carbide particle system, and also a thermal conduction study. SEM image of heat-treated sol gel treating alpha silicon carbide particles subjected to organic solvent wash revealed the presence of spherical particles on figure 6A as a secondary growth mechanism. Figure 6B shows the presence of a uniform flaky coating on the surface of the reinforced and delamination of the coating. The micrograph demonstrates non-uniform coverage of large surface areas, whereas 6C demonstrates extensive coverage of the alpha silicon carbide particle surface. The result of SEM or EDX analysis did not indicate the presence of fluorine and related process impurity in figure 7. As shown in figure 8A until 8F, the SEM micrograph of sol gel treated alpha silicon carbide particles subjected to organic solvent and deionized water wash clearly show the formation of a thin flaky layer of ceramic oxide coating. For figure 9 shows that the SEM or EDAX confirmed the absence of fluorine elemental peaks, which is consistent with the earlier reported results for its counterpart. The following conclusions were reached as a result of experimental trials and characterization studies. Firstly, precursor surface treatment is critical in the quality aspect of the sol gel coating process. Secondly, it was discovered that the heat-treated and sol gel coated alpha silicon carbide particles did not contain any residual process-related impurities. This may be due to the surface pretreatment method used. Lastly, the result reconfirmed the suitability of the sol gel process methodology for the interfacial design of copper composites with the alpha silicon carbide particle as the reinforcement.